So in the last video, we looked at 3D maps and cold fronts. The 3D maps look like this. And now we're going to move that into surface maps so you can feel more comfortable reading surface maps. We started that in the last video, but we're really going to delve into it now. What you're seeing here is you're seeing an axis between x and x prime that is met between an axis here of x to x prime on the surface map. So we're moving from 3 dimensions to 1. You are seeing the frontal line in about the same direction that you've got the frontal line here. And you are seeing station models along the frontal line and in the back, similar to the very simplified station models on the 3D model. Let's go into it a little bit more and let's delve into the increased information that we have on the surface map. To really get into our surface map, I needed to tilt this for you so that you could read all the numbers from left to right. So this map has now been tilted a bit. Banjo Guy is still down here. He's waiting for the cold front to come at him. And when we see this map, we have so much more information on it. And the first thing we're going to look at is the pressures that are on it. So what you're looking for is a pressure trend, because the pressure trend will tell you a lot about where the front is. And what I see here is while Banjo Guy is waiting for the front to come at him, before the front arrives, you see an increase in pressure and then a real steep decrease in pressure, similar to rising before a greater fall. Why is that happening? That is happening because this warm air mass that is by Banjo Guy realizes that the cold air mass is coming at it and it's starting to head up and into the atmosphere. Remember, rising slow, clouds and snow, surface low. So that is why the pressure is dropping before the cold front comes in. As the cold front does come in and as you get closer to the front line as it's coming at Banjo Guy, you see that the pressures are definitely continuously falling in that area. That is because that warm air in your warm air mass has been lifting. Remember that when we say rising slow, it's going to be a surface low. And you're noting that the clouds are building in that area as we've been talking about the altocumulus and the cumulonimbus as well. In back of the front, as the front has come through, we see in here, for instance, we see a fall and then a rise, a fall and then a rise in pressure, a rise in pressure. And what is happening there? After the front comes through, after this dense air comes through, the pressure rises because the cold, dense air is in place. And in fact, the pressure will continue to rise quite a bit because the mass of the air mass is coming through. You're just catching the edge of the cold air mass here, but the mass of the air mass is back in here. That is going to be consistently higher pressure in that area. You may have noticed that there is a kink in these isobars. Let's go over where the isobars are because they tell us where the front is. This isobar, I don't love this map. You know how we have 4 millibar increments and they should be in even numbers. This one has a 4 millibar increment at 1013 and at 1009. Very strange. I would have made it 1008 and 1012, but that's what we got. When we work in these 4 millibar increments, you may see here that this comes down here and has this little kink to it, and then it keeps going and becomes a 1012. Look at that. Oh, I see what's going on. It's 1012. It goes past a 1013 station model. You're right. This is a 1012. And here's a 1008. Okay, it just goes past a 1009 station model. That's in between the 1008 and the 1012. That makes sense to me now. There's the 1008. But look at, I've got a trough in here. Because normally if I had a nice smooth line, I would have a nice smooth line like that for 1008, right? And this would be 1008 right here. But now it's saying that I could have a 1007 right in here because I've only got 1008 here. And look at this. If I had a nice smooth line for 1012, then I could have 1012 right here. But look, I've still got 1011 right there. I've got a trough of pressure right by the frontal line. Why do I have a trough of pressure there? The kinks in this mean a lower pressure at the frontal line. Let's explore that a bit. That is due to the drama of the cold air mass that comes in so quickly and that sends the last of the warm air jettisoning up, really dramatically lowering the pressure as the front comes right through. So that is an idea of the short distance and the short time frame for these fronts. And that kink that you see when you create isobars, that kink will tell you exactly where the front is. And we'll look for that in some of our labs. Precipitation you can also see on the surface maps as well. And you see that you have a thunderstorm notation in here. It's the only thunderstorm notation you have on this surface map. You see precipitation over here. You see some precipitation over here. This is the only thunderstorm notation, and it happens to be where the gradients are tightest, where you're having the most pressure change and the most temperature change. So in a very short distance, you go from 50 to 39, and look, you've got a very, very narrow distance between pressure changes between the 1009 and the 1010. You've got broader here between the 1007 and the 1008. You've got broader here between the 1011 and the 1012. So where these are really tight, that's where your thunderstorm is. You've also got wind speed changes, and those wind speed changes, you see them here. Some of the highest winds are right behind the front. And that is due to the difference in the pressure and the pressure gradient force in that area. So you're going from 1009 to 1010, and it is really speeding up when that gradient is tight. That's your wind speed. And I already went over that with you. I want to talk about the passage of the cold front. Sometimes it's not even dramatic in temperature, especially during the summer, because we don't get a whole lot of cold air from Canada in the summer. Canada is actually quite temperate, 60 and 70 degrees up in Canada. I was up there last summer. So you don't get a lot of temperature changes in the summer, but you do get often changes in dew points between the two air masses. And if you live in Oklahoma and Texas, you are all about the dew points because the dew points will predict your tornadoes. So let's get into that a bit. That's exciting too. You will see in here differences in the dew point. Remember, dew point is below temperature on the station model. 48 degrees, very, very close to 50 for the temperature. Very tight gradient, very, very moist air. We call it juicy air in there. Air that is ready to precipitate right out. And 48 degrees is from the moist, warm side versus 37 degrees, 11-degree drop on the other side of the front. Another tool for finding fronts is to look for these dramatic changes in dew points. You see it there. And this is another way to find a front. You can look on Doppler radar, which is just looking at sound transmission through precipitation. So now that we've gotten to the precipitation, you can see that this is the same storm on Doppler. So now you've seen it in 3D, you've seen it in surface maps, and you've seen it on Doppler maps. It's a pretty severe storm right there. You can see the thunderstorm that's right here. That was noted on Doppler. That surface map is a little bit delayed, so you don't see everything on the surface map. I could go into this cold front table, but we have reviewed pressure and precipitation and dew point on it. We reviewed other characteristics in the 3D graphic that I had. I suggest that you go through your text, find this, and review it before the cold front passes with Banjo Guide, while it's passing, and after it's passing. It'll all make sense to you now. One other thing I wanted to go over with you is backdoor cold fronts. And those are nor'easters. And I had mentioned it on the air masses before. So I just want to go over the dew point differences between the maritime tropical air mass that comes up from the Gulf of Mexico at 58 degrees for a dew point and 45 degrees for this dew point on the maritime maritime polar out of the North Atlantic. So here's an area where you really see the cold temperatures and the cold dew points and the warm temperatures and the warm dew points. These notations on a surface map indicate that the atmosphere is right for a nor'easter. Usually happens in the fall and spring. And I'll see you on the warm front side. That's exciting too.